So let's continue with discrete logarithm problem. So the digital signature algorithms we use in cryptocurrencies actually use elliptic curve cryptography, but their security depends on the discrete logarithm problem. So think about the number g. It can be very small. It doesn't have to be big. So if you take a 8 power of it and obtain b, for an attacker knowing b and g, capturing a should be hard. So this is the discrete logarithm problem. So I haven't explained what a group is or what a generator is. Actually, in the week of digital signatures, I will give you every algebraic definition, and it will be very clear and very easy for you to understand what is going on. But let me tell you how this works in practice. So assume that you have a g here as 3. So I chose x and take the x power of 3 modulo this number, and then obtain the result and ask you to find the value x. So we believe that this problem is hard. So going one way is easy because here we are performing modular exponentiation. It is very easy to perform regardless of how big x is. But finding x from here is not that easy. And in reality, we choose this number prime to make the problem even harder. And you might think that you might ask if this number is prime, but the answer is easy to see. It is not a prime number because the last digit is 5. So you can divide this number by 5. And if it is not a prime, if you factorize it, then it is easier to find x because you solve this problem for those factorizations, then use the Chinese remainder theorem to find x. It is not actually important for this course, but know that if you choose a very huge prime number, a lot larger than this one, finding this x is a hard problem. Okay, so in this case, the answer is this, but trying one by one is not an option in this case. Okay, so if you know this problem is hard, so in this case, as a group, I used numbers modulo this number, right? But there are other groups which makes this problem even harder. For instance, think about an elliptic curve. It is just a mathematical object like this. And strangely, the points on this curve can be used to create a group, an algebraic group. So an elliptic curve looks like this, depending on your choice of A and B's, like here. The shape of the curve changes, but the main idea does not change. And strange enough, I can define a very strange addition operation on the points of this curve. Okay, so it is very strange, but the addition is defined as follows. So just think about 2 points on the curve, okay, and you want to add them. Addition operation is defined as follows. Draw the line passing through these 2 points. Okay, so if you do that, it has to intersect the curve at a 3rd point. This comes from actually the equation from the elliptic curve. So it has to intersect the curve at a 3rd point. Just take the reflection of this point with respect to x coordinates, it is this, and say that, okay, this is p plus q. Very strange addition operation, but it works, okay? So every element has we have an identity element. We claim that there is a point very far ahead at the infinity. It is vertically somewhere at the infinity, and it works like an identity element. Like in addition, 0 is the identity element. If you add any number to 0, you obtain the same number. In this case, if you add this point to the point at infinity, then you have to draw a vertical line. So it passes through P. It passes through that point at the infinity. It intersects as a 3rd point here. And if you take the reflection of it, you obtain P back. As you can see, the point at infinity works as an identity element. And the inverse of every element is just a reflection here. So if you add P to minus P, you obtain, the point at the infinity, which is referred to as this point at infinity or 0, depending on how you define it. And if you want to add a point to itself, then you have to draw the tangent line passing through that point. It has to intersect that place. So this is 2p. So as you can see now, I can define some kind of a multiplication. I can add a point to itself, for instance, k many times. So the point is p. If I add p to itself k many times, I obtain k times p, right? So if you go back to the discrete logarithm problem, instead of g to the a here, this is for multiplication. In our case, it is addition. So I will define a times g, or if you choose the point as p, you will say p. So I will choose a point, add it to itself a many times, and obtain another point, and I will ask you how many times I added. So I will ask you to find a. So this is why I can use discrete logarithm problem on elliptic curves. This is not a multiplication operation. This is an addition operation. Okay, so a group is defined with a set of elements and an operation. The set of elements are the points on this curve. The operation is addition operation. But if I somehow define a multiplication operation, then you can do it. But again, I will explain everything when I define what a group is. But the group has to have an identity element with respect to the operation that you are defining. In this case, it is addition. Every element has to have an inverse. And if you add two elements, the result has to be inside the same set. So another point at the curve. So it is a very weird looking thing. So you might think that we were talking about Bitcoin, how things have come to this. So whenever you choose a private and public key as a Bitcoin user or an Ethereum user, you are actually choosing points on an elliptic curve. Okay, it might be surprising to hear it for the first time, but this is what happens. Whenever you sign something, you are using elliptic curve cryptography to sign it. Okay. So I will move on again. This, of course, these drawings are from R square. So I look at the real numbers as the roots of this equation. But if you do this like this means that there are infinitely many points on this elliptic curve. But we are living in a finite world. We have to transfer our messages to finite elements. So for this reason, we actually look at the points over some group. In this case, that's 8 and 9 as an example. So instead of infinitely many points like here, you end up with small number of points here. So addition actually defined here. But of course, there is no direct relation with the geometric object like here and here. This point is not reflected as here, okay? Because here we are drawing it with respect to R and R. Here the points are coordinates of X, Y, which are actually an element of Z8 and 9. And if you don't know what Z8 and 9 is, it is numbers from 0 to 88, 0, 1, 2, 3 until 88, okay? So we are performing operations here. So at the point when we talk about digital signatures, I will explain what a group is, how do we define these operations, and so on. Then everything will make sense. Again, Bitcoin uses an elliptic curve, but almost every other cryptocurrency uses the same elliptic curve because they always use the source code of Bitcoin, the Bitcoin core, okay? So whenever you use Ethereum, you also use the same elliptic curve. And this elliptic curve is not a NIST standard. So that is another thing we have to discuss. And this is a huge misconception. Google it and write the name of this elliptic curve, Bitcoin elliptic curve, you can say it that, and write if it is a NIST standard, and you will see a lot of pages saying that it is a NIST standard. There are even books published a few years ago saying that this curve is a NIST standard, but it is not. So there's a lot of huge misinformation on the internet. I will explain why it is not a NIST curve, but why it is still secure. And I can also give you an inside information. NIST in the following revisions will include this curve in their document in order to have interoperability with this kind of blockchains. But so far it wasn't included in any of the NIST documentation. Okay. So Satoshi, instead of choosing the NIST curve, chose a different curve, and we will talk about it when we talk about security at the end. Okay. So let's move on to post-quantum cryptography. So I told you that the discrete logarithm problem, or if you talk about the problem on elliptic curves, it is referred to as elliptic curve discrete logarithm problem. These are hard problems. There's also integer factorization problem, which is used in RSA. And actually, in this course, we are not planning to use RSA, but RSA accumulators are used in some of cryptocurrencies. So we will briefly mention what an RSA algorithm is. But we rely on the hardness of the following problems: integer factorization, discrete logarithm problem, or the elliptic curve discrete logarithm problem. But the problem is that if somehow somebody can build a very huge quantum computer, we can solve these problems in polynomial time. So this means that you can steal everybody's cryptocurrencies. But of course, if somebody builds such a computer, instead of stealing everybody's cryptocurrencies, you can also use it to listen to everybody in the world, because all of the internet communication, the security relies on the hardness of these problems, like the Diffie-Hellman key exchange, RSA, or AlGamma. So currently, IBM achieved 128 qubits. So quantum computers, their power are measured with respect to the amount of qubits they have. So this was the news from November. Maybe somebody has something better. But to break 80-bit security, for example, RSA 1028, you need to have 2048 qubits. But we have to make a distinction here. So IBM says here they have 127 qubits, but we have to ask, are they real qubits? Because sometimes there are noise. So in order to avoid those noise, maybe you need to have 1.5 million qubits so that it will work as real 2048 qubits. Okay, so this is why currently you hear a lot of news about quantum computers as if they are doing fantastic things, but in reality they do nothing. One of the main explanations is that. Okay, so there's currently a huge hype, but most of the time all of the newspaper headlines are sometimes wrong. Okay, so for this reason there is a Twitter account called Quantum Bullshit Detector. So if you are using Twitter, I recommend you to follow it. Whenever a paper is published about quantum computers, he declares if it is bullshit or not. Okay, so nice thing to follow. So NIST is organizing a post-quantum cryptography competition. It is about to end. I think the finals are known or will be announced in a few days, but people can guess what they are. But the result of this competition may be not directly applicable to us, because if we want to change the elliptic curve cryptography in Bitcoin and replace it with the winner of this post-quantum cryptography competition, and if we choose a signature algorithm from this competition, maybe it wouldn't fit to our needs, because as you have seen, for instance, Bitcoin block size is 1 megabyte. So now we are interested in how large the signatures in these post-quantum algorithms, and most of the time they are really huge. So there are more things to be considered here. And as far as I know, NIST is going to call for another, not a competition maybe, but call for algorithms for signatures and so on. So the current status is not good enough to replace cryptocurrencies with a post-quantum secure signature algorithm. So there are things to be done here, and we will talk about them later. But of course, recall that adding a new cryptographic algorithm to blockchain requires a soft fork. But instead of adding, if you want to remove the previous ones, then it may cause a hard fork. Okay.